Okay, what I have here is a wooden stick of uniform mass. Mass m, length L. The center of mass, of course, is midway between point A and point B. The distance between here and there is half of L. Now, to begin with, the left edge, point A, of this wooden stick rests right on the edge of a table. Okay, so it's barely touching the edge of the table, and I'm holding this this ruler or this stick with my hand so that it is momentarily horizontal and at rest. Okay, so that's the initial situation. It's not moving yet. It's horizontal, and there is a supporting force here, provided here. Let's call it N. I know it's upward, but I don't know how much it is. Now, what I'm going to do is I'm suddenly letting go of it. So obviously this thing loses balance. It's going to start to swing down. Okay, it starts from zero velocity, but it's going to start to swing down. At this moment, the moment you release the stick, okay, the moment you release it, it's still horizontal and at rest, but it has already lost dynamical balance. It is ready to rotate. What I want to know is, at this particular moment, what is the value of alpha? You know it's going to rotate about point A, right? What is the value of alpha? And also I want to know, at this moment, what is the supporting force N? What is N equal to? At the moment you let go of it. Okay, this problem actually consists of two parts, two aspects. One is, you know the thing is rotating about point A, which is about to rotate about point A, that is. Okay, so that is rotational motion. On the other hand, you can always apply Newton's second law for translational motion for the center of mass. Okay, whether it's an extended object or not, whether you know, it's a rigid body or not, it doesn't matter. You can always use F equals ma for the center of mass. So that is how we describe the motion of the translational motion of the center of mass. Okay, when you apply the torque theorem, there's the thing. When you apply the torque theorem, torque equals I alpha. It makes a difference which axis is the axis of rotation, right? When you switch to a new axis, you know torque is going to change because the lever arm changes, and you know even I changes, the rotational inertia changes. So the question is, about which point can I apply the torque theorem? Can I apply the torque theorem for the rotation about point A, about the center of mass, or point B, or any other point? Well, it's a long story, but let me tell you what the answer is. You can verify that through various examples yourself, and that is, there are only two kinds of points you can apply the torque theorem to. You cannot apply to just any point. Okay, the first type of point is a stationary point. That point itself does not move. The velocity of that point is zero. Example, right here, point A. You can do that. The whole rod is rotating about point A, so you can do that. Use point A as an axis of rotation, apply torque theorem. Another type of point is the center of mass. The thing about the center of mass, it's so unique that it doesn't really matter whether the center of mass moves or not, whether it accelerates or not. You can always apply the torque theorem to the center of mass. You write torque equals I alpha, calculated about the center of mass, and I also calculated about the center of mass. So it's either going to be a stationary point or the center of mass. Okay, what we're going to do for this experiment, for this particular example, is I'm going to apply two things, both the F equals ma for the center of mass, that's for translational motion, and the torque theorem. And when it comes to torque theorem, let me apply it to point A and to the center of mass to see whether I get the same result. I should. Okay? And then by comparing these two, you can tell, you can draw a conclusion for yourself, which point should I apply the torque theorem? Even though you get the same value, same final answer, which point do you think gives you an easier answer? Okay. Do not apply the torque theorem to point B, because that point is not the axis of rotation, nor is it the center of mass, and it is ready to move. Okay, it is not balanced. We can apply it to a stationary point or the center of mass, but not point B. So let's see now. First of all, about the translational motion, let me focus on the center of mass for translational motion. Okay, so I have F equals ma, right? Let me draw the remaining force, And that is, of course, the weight going through the center of mass, mg. Okay, so I have N and I have mg. These are the only two forces. So, choosing downward is positive, I have mg minus N. What is that equal to? That is the net force in the vertical direction. That should give you mass times acceleration. It is not just any acceleration, but the acceleration of the center of mass, of that point. Okay, that is all there is to it when it comes to Newton's second law for the center of mass. But you see that is not enough because I don't know what N is, nor do I know ACM. So this formula alone does not tell you the whole story. I must also look at the rotation of the object. At this point, I have two choices. A, I can use point A to apply the torque theorem, or B, I can use the center of mass to apply the torque theorem. Let me do both of them, and let's see which one is better. If I use point A to apply the torque theorem, let me ask you this. What is the torque provided by the force N? Well, here's the thing. You have point A right here, right? The torque goes right through it. I mean, the force N goes right through it, like this. This is N. What is the distance between the line of action of the force and the point of interest, which is A? That distance, as you know, is called a lever arm, right? And since the force goes right through it, what is that lever arm equal to? 0, right? So therefore, what is the torque provided by N about point A? That is 0 because the force goes right through it, therefore the torque about point A is 0. So you don't have to worry about that torque, because even though the force is 0, the torque is not. I mean, the force is not 0, the torque is 0. What's left, of course, is only the torque provided by mg, the weight. Now, there are two types of torques for a fixed axis rotation. This torque can encourage clockwise acceleration, or it can encourage counterclockwise acceleration. Okay, I can call one of them positive, the other negative. Let's say we call this positive as clockwise. So since mg provides a clockwise angular acceleration, it's a positive torque. Okay, what is the torque equal to? By definition, torque about point A. Okay, mg, that's the force, times the lever arm. What's the lever arm? Well, here's the line of action. The line of action, and here's the point of interest. You drop a perpendicular from the point of interest to the line of action. That distance is the lever arm, and what's that distance from here to there? Isn't that half of L? Okay, again, that is all the torque there is about point A, because N has no torque. According to the torque theorem, torque about point A should be equal to rotational inertia about point A times alpha. What is the rotational inertia about point A? It's a uniform rod, mass m, length L, about one end. Now, we did that calculation before. It's 1/3 ml squared. Okay? And then times alpha. Now, what can we get from the second formula? The second formula tells us what alpha is, because alpha is the only thing I do not know. Okay? As a matter of fact, let me solve for alpha easily. What's alpha equal to? Alpha equals 3/2 and then g over L. That's alpha. Okay, that's alpha. And once I know alpha, can I find ACM? You know, the linear acceleration and the angular acceleration at this point, of course, they're related. Okay? Because, you know, the velocity at this point, the speed at this point, I should say, the speed at this point, v is equal to omega times this length, which is the radius of the circular motion of that point, right? So when you take derivative, don't you get tangential acceleration equals alpha times r, r being the distance from here to there, right? So it's A equals alpha r. We got that before, remember, for the kinematics of rotation, except r is the distance between here and there, okay, because we're concerned about the center of mass movement. So I have ACM equals alpha times L/2. Okay, let me highlight it. I get equation 1, 2, and 3. Where do these come from again? This is for translational motion. This is for rotation about point A. And this third formula is the connection between translational quantity and rotational quantity. Okay, so this is a kinematic consideration. Both of these are dynamical equations for translational and for rotational motion. With these three equations, we can solve for everything we want to know. For example, if I got alpha, right? You plug it in here, what's ACM? ACM is alpha times L over 2, so ACM becomes equal to L over 2 times 3G over 2L, so the answer is 3 over 4 G. You notice it's less than G. Why is it less than G? Because if it were equal to G, this rod would be in free fall. The only force exerted on it would be mg, right? But right now, there is an upward force. Therefore, the net force is less than mg. Therefore, the acceleration is less than g. How much less than g? 3/4 of g. What happened to the other 1/4? It's because there's a force upwards. Okay, you can easily tell then the force upwards must be 1/4 of g. As a matter of fact, when you plug this, you plug this ACM into here, this side is 3/4 mg. This is mg, so what's n equal to? That must be 1/4 of mg. Okay? So that's what happens. At the moment you let go of it, this thing is ready to fall. The acceleration of the center of mass at this one moment is equal to 3/4 of g, and the supporting force must be 1/4 of mg. So again, the way we solve this problem, if we look at three aspects. We looked at the translation motion about the center of mass. That's one. We looked at rotation about a fixed axis, which is point A. We also looked at the connection between linear motion of the center of mass and the angular acceleration of the object. Okay, so please make sure you know how to put all these three pieces together. Okay, we're going to do this a little differently now. We're going to write the rotational equation about the center of mass. Why are we interested in doing that? Because I want you to see for yourself, you get the same answer, first of all. And secondly, let us compare this new approach with the previous approach of choosing point A as the axis of rotation. All right, so let's do that. This time, you know, I don't have to rewrite this first equation. It's still the same. It's just translational motion about the center of mass. But the second equation, I have to rewrite it. I'm using the center of mass as my reference point, okay, to find torque Cm. This is the torque about the center of mass, equals ICM times alpha. Alpha is always the same, no matter who's looking at it. Okay, alpha is always the same. Now, what is torque Cm equal to? Does gravity provide any torque about the center of mass? No, because it goes through it. Okay, the lever arm is 0, right? Now, you only have an n left. This n, about that point, also encourages the clockwise acceleration. Of course, that's true because alpha is still the same. What is the torque of n? It's equal to n times the lever arm between the line of action, the distance between the line of action and that point. That distance is, again, L over 2. So n times L over 2 equals the torque about the center of mass, and that equals ICM times alpha. What's ICM? ICM is the rotational inertia of the rod at its center, and that is not 1/3 ml squared anymore. It is 1/12 ml squared. If you review our previous lecture, ml squared, 1/12 ml squared times alpha. Okay, you can find a formula for alpha now. Okay. You can find a formula for alpha, or you can just get rid of n if you prefer. So we can solve for n. What's n equal to? N equals to m alpha L over 6. Right? Okay, ml alpha over 6. Now, you notice that doesn't quite solve everything for you because you still have two unknowns, n and alpha. Unlike here, when we took center of point A, we immediately got alpha. Here, we only got the connection between alpha and n. Of course, I can still solve it. You know, I can continue to work it out, which I will do in just a minute, but you can immediately compare these two approaches to see which one is better, which one gives the quicker answer. Obviously, the first one does. Why does it give you a quicker answer? Because in the first one, when we chose that point, point A, as our observation point, we immediately eliminated one unknown, which is n. Here, we choose the center of mass. We only eliminate something we already know, which is mg, but we left this unknown, which is n. So here is how we choose our observation point. If we had a choice between this point and that point, a better choice would be point A, because that way we eliminate an unknown force. How do we do that? By making sure that force goes through the point of observation so that its lever arm is equal to 0. This is how we eliminate the force without having to worry about it, because the torque of that force is equal to 0. Okay, so that's the trick. If you see a whole bunch of, say, suppose you see a whole bunch of forces, unknown forces, and they happen to pass through a point. They happen to intersect at a certain point, and that point is fixed. What do? Jump on it and make it your point of observation to apply the torque theorem, okay? Because that way, those forces will not appear in the equation because the torque is equal to 0. So, we have this comparison. But let me convince you that even though this takes a bit more time, we'll get the same answer eventually, okay? Let's see whether this can be done. You know you have alpha here. If you want to plug this in back in the first equation, that still doesn't solve the problem because you still have an extra alpha here. But don't worry, alpha is related to ACM, right? It's related to ACM, alpha L over 2. So alpha equals 2 ACM over L, 2 ACM over L. So let me plug that in. Okay, so m over 6 L times alpha. Alpha is 2 ACM over L. 2 ACM over L. Okay, so what do you have here? You work it out, that's 1/3 m ACM. Okay, that's m. Now that's better, because I can now plug this n equals 1/3 m ACM to the first equation here, which will give me ACM. Okay, let's do that. So mg minus n, which is 1/3 m ACM, that equals to m ACM. There we go. Let's solve for ACM. You move that 1/3 over there, that's 4 over 3. Right? 4 over 3, cross out m and flip it over, you get ACM is 3 over 4 G. That is exactly the same answer as we got here. ACM equals 3/4 of G. Once you get ACM, of course, you can find n, right? You can find n because, you know, n is 1/3 m ACM, so n would be 1/3 times 3 over 4, that's 1/4 mg. And of course, once you get n, you get ACM, you get alpha. Everything is done. You get the same answer. But clearly, there is an advantage of taking that point, and I hope that you learned from this special example. You won't learn a general lesson where you choose your point of observation smartly so that you can simplify your calculation.